Perfect. All right. Thank you, everyone. Yeah, normally I just talk about my specific sub niche of physics-inspired machine learning. But I thought today, since this is sort of a general seminar course, it would be nice to talk about kind of the bigger picture. And if any of you are working on your own data-driven projects or machine learning projects, I thought I might throw out some ideas of how to incorporate physics that we've spent many, many years learning directly into your network or directly into your project so that you don't have to waste any learning time relearning what we already know. How do you make your applications learn interesting things instead of redundant physics? So I wanted to start with this picture here. So I went to Adobe Firefly just this last week, and I asked it to generate a picture of a tilted coffee cup with coffee inside. What do you notice about this picture?
Physically impossible.
Sure, yes. Why did it do this, do you think? It's probably because the vast majority of coffee cups it's seen have had the coffee level with the cups. So it incorrectly assumed that when it rotated the cup, the coffee would rotate with it instead of adjusting and undergoing some dynamics there. Technically this could exist, but it would immediately move. This is not an equilibrium configuration. And the network doesn't know that. It's just trying to generate a coffee cup with coffee in it and tilt it like I asked. So there are questions, how can I, obviously this is just image generation. It would probably be very, very difficult to build in a hydrodynamic solver into this in order to generate simple pictures. But I want you to think about what are fundamental changes I can make to my architecture or my processing, which ensure that some aspect of the physics is just captured automatically. So what is physics? I think it's important to answer this question. What are the principles that actually go into physics? How can we modify our networks to do something automated? And I think that one of the most important things is that every measurement that you ever take in the physical sciences has a unit associated with it, right? So if you took physics 1, you spend the first couple weeks just learning about mass, length, and time, and how to construct characteristic timescales, how to do dimensional analysis, figure out the dimensions of different things you would build. And in particular, there's the Buckingham pi theorem, right? The Buckingham pi theorem, if you don't know, states that every function can be constructed as the product of a characteristic scale and a function of an arbitrary nonlinear function of dimensionless quantities. So if I want to have a function which is velocity as a function of time, this has to be, in order to be physically valid, it has to be the product of a constant characteristic v, which has the units of speed, and then a dimensionless, potentially nonlinear function of a dimensionless time. So here I have my time divided by a characteristic time scale t. And this has to be the case. So this makes grading physics exams really easy because if your answer isn't of this form, I immediately know it's incorrect. I don't have to read the work you did. I try to, but you know, you can tell when a mistake has been made if this form isn't reached. So just to make this concrete, let's say we have constant linear acceleration. V is v naught plus at. Hopefully you've seen this formula before. How can we massage this into the form above? Well, we have a characteristic velocity. What's the characteristic velocity? What is the capital V in this scenario? What is the only constant in this equation with units of velocity? Cool. V naught. Very good. So we can say for certain this formula has to be a dimensionless quantity times V naught, and we can write it as so. So all you have to do is factor out the V naught from both terms, and in this case, f turns out to be a linear function, but we've obeyed the Buckingham pi theorem. So here our characteristic timescale is the ratio of V naught to A, but we could have actually inferred, even if we didn't know any physics, so to speak, we didn't know any equation, we could have inferred the form of the equation for V of t directly from the constants that we had available to us, even if we didn't know V naught plus at. And I want to say that if doing dimensional analysis is very difficult, there's this really cute paper that was published in Nature Comp, was it Comp Sci? Just a couple of years ago where they automated a small neural network layer to try to find the dimensional scaling of everything and do this for you in an automated fashion. The next thing I would say is that physics describes relationships between derivatives. If you're not doing derivatives in your data, it's not quite physics. So here's a huge collection of four equations that you might encounter in a physics class. So you have the famous F equals ma, where a is the second derivative of position with respect to time. We have a Poisson equation, perhaps. You're taking a second derivative in space of a scalar field. So this is in electrostatics or gravity. This is how you determine the gravitational field. The Dirac equation, which applies to relativistic quantum mechanics. Again, it's just a differential equation. I mean, when you make it a quantum operator, there are additional rules you have to keep track of. But at the end of the day, we're looking at differential equations, and then, of course, the Einstein field equations, which are perhaps one of the greatest triumphs of theoretical physics. So we really care about taking derivatives of data and matching those derivatives in some way to compute relationships. Also, these derivatives often produce conserved quantities. So if you have a system governed by F equals ma, a pretty generic feature based on assumptions of the force. If I assume the force only depends on the distance between two bodies and only acts in the direction in which they're displaced, I can say fairly generally there's three conserved quantities. There's an energy, which doesn't change in time, a total momentum, which doesn't change in time, and an angular momentum, describing how everything rotates. And these conserved quantities tell us quite a bit about the physical nature of the system that we're looking at. And the last point I want to make are that these relationships often have a high degree of symmetry to them. So F equals ma, let's say I have a box that performs an experiment and through that experiment determines that the laws of physics are F equals ma. If I take that box and I do the experiment, and then I wait 5 minutes and do it again, I'm still going to find F equals ma. Time translation does not change the law of physics. I could also pick the box up and put it 10 feet to the side. I'll still get the same underlying laws of physics. I can rotate the box. I'll still get F equals ma. I can even put the box on an airplane, right? It can be moving at hundreds of miles per hour. It'll still find F equals ma, right? So there are classes of transformations I can apply to my data and still reach the same overall observations. So in terms of how to build this into data-driven methods, I wanted to say one more thing about symmetries, which are these last 2 points are intimately connected, and we've known this since the early 1900s. So Noether's theorem is that symmetries generically produce conserved quantities. This is, again, one of the huge theorems of theoretical physics. And in fact, many of the conserved quantities, which I described before, directly follow from the symmetries of Newtonian physics. So time translation directly gives you energy conservation, spatial translation gives you momentum, rotations give you angular momentum, boosts give you actually your center of mass having a predictable trajectory. It's a really bizarre conserved quantity, but that's where that comes from. And one thing that physicists worked out is that electrical charge also, the conservation of electrical charge stems from an internal U1 symmetry. And working out the standard model, you get the conservation of many other quantities in particle physics, which similarly just stem from Noether's theorem. So there's a very deep connection. And what I want you to take out of this is that if you're trying to model a system with a conserved quantity, be it density, like mass conservation or momentum or energy conservation, incorporating your symmetry with 100% fidelity is a way of getting close to conservation. If your approximation for your numerical approximation also has time translation symmetry, you are almost certainly guaranteed a kind of energy conservation, even if that energy isn't a one-to-one match with the one that you intend to keep track of. So Noether's theorem is very helpful. And also, this was the AI art that I attached with today's picture. In general relativity, you have an infinite dimensional symmetry group, which is the diffeomorphism group, where you can take your coordinate system and just twist it and stretch it and do whatever you want to it, and your equations are unchanged. So I call this a normal apple because I like to think it is a normal apple, and it's just been twisted in our chart, and so it looks confusing. But the fact that it's an apple is an invariant of that. And a curiosity is that I guess the sidebar here is covering some things up. Because of Noether's theorem, in general relativity, you get an infinite number of conservation laws because you have an infinite number of symmetries. It's a nice feature of this. You can see Bergman for details on that. Okay, so now that we've discussed what physical considerations I think are very pervasive and should go into your data-driven applications, let's talk about how to actually use those considerations. So physics equations have units, right? The measurements we have are unit-fold quantities. And so if you're building a neural network, I would say only use non-dimensional data as input and output. This will automatically satisfy the Buckingham-Pi theorem. A few weeks ago, there was a fantastic talk on modeling near wall flows. So this was the neural network that was presented. I took it from the JFM paper. And you can see in the inputs and the outputs, there are these maybe at first glance bizarre fractions that go into them. But you can check these are carefully constructed non-dimensional quantities using the viscosity and the distance to the wall to non-dimensionalize everything and allow the neural network to extrapolate among many different scales. Similarly, the output is outputted in non-dimensional form. And if you want the actual physical quantity that you would measure, that would be influencing your aircraft, you then just rescale it by the physical parameters from the outside. This is perhaps almost an obvious point, but I think it's really important to keep in mind. And I was thinking about this a lot, and I think that sort of as a contrapositive to the Buckingham-Pi theorem, if your network is incapable of taking this form, it must fail to generalize in some parameter regime because you cannot have learned the correct equation globally. The next thing, so we need to think about how to do derivatives. We need to handle derivatives and match them in some careful way. And unfortunately for us, real data is very noisy. We can do simulations with 0% noise, and we can take derivatives with high order finite difference stencils or spectral methods. But all of these are susceptible to perturbations added locally. So as an obvious demonstration, I've taken sine of x and I've added 2% noise uncorrelated to it. And qualitatively, it looks like sine of x. You can imagine filtering this data. But without filtering or anything careful, if I just went ahead and computed the finite difference derivative, you can see what I should get is in red, but because of the noise, I get an amplification in my error. So I started with 2% noise, and now I have considerably more than 2% noise after just attempting to take a single derivative in a not very sophisticated way, but this is a pervasive problem in estimating derivatives. And as I take higher and higher order derivatives, this problem will just become exacerbated. By the time I look at the sixth derivative, certainly almost no influence of my true underlying data will be left. It will all just be noise. So there's an effective maximum derivative you could imagine taking before noise takes over. So what do we do about this? I mean, you could imagine smoothing your data, but what if your data has an interesting sharp peak and you don't know if that's statistical noise or if it's a flare around an accretion disk in a black hole? How do you tell what's noise and what's actual underlying features of your data without getting your hands too dirty with statistics? And I would say that the best tool for the job currently, as recent literature is saying, is the weak formulation. So if I need to evaluate the derivative of a field U and compare it to some target, let's say I'm trying to solve a first order differential equation, the x derivative of U equals V, and I want to evaluate that. Instead of evaluating the x derivative, what I can do is I can multiply both sides of my equation. Here, I'm just considering the x derivative. I multiply it by a weight function phi that I know analytically. And then I just do integration by parts. I move the derivative from my noisy data U, and I move it onto this noiseless, perfect weight function field phi. So here's a picture of it. Typically, we take these to be envelope polynomials in practice. You can also multiply them by Fourier modes at sines and cosines. Really, the only important point is that you'll notice that here at the edges of my domain, so this integral is a bounded integral, right? You're going to do a Riemann sum to approximate this integral. In order for the integration by parts to not pick up a boundary term, I need my weight function to vanish at the boundaries. So this is something that's both a quality of life decision. It also impacts the accuracy, surprisingly, of the numerical quadrature. So by choosing weight functions which vanish and have high derivatives that vanish. So here I'm choosing the value of my weight function and its first 7 derivatives to vanish on the boundary. And by doing that, I actually get 8th order convergence so I can control how exponentially convergent my integrals are just doing a simple Riemann sum. It's kind of a counterintuitive fact. And I guess the difference between these two approaches is that if I have a lot of noise and try to estimate the derivative, the noise gets amplified. If I try to compute an integral and I have noise, the noise gets averaged out. So they're accomplishing the same motivation, but it's much more robust. And this has been used for experimental data in several cases to do model discovery. And also in, I guess I suppose I just have model discovery references there. Oh, one of them, the Zhang et al. That one is solving high dimensional PDEs. So solving the Laplace equation in 20 dimensions and using the weak formulation to do this with neural networks. It's a very interesting paper. Any questions on the weak form? So as a quick demonstration of the weak formulation and its robustness to noise, we took some data from the Johns Hopkins turbulence database. So we took a snapshot of three-dimensional turbulence for about, I think, 100 time steps. I think it was a 64 to the fourth cube, 64 to the fourth hypercube of data that we pulled from it. The true resolution of this simulation is staggering, with approximately 1,000 grid points per dimension in 4 dimensions, and a really tiny kinematic viscosity. So not a whole lot of dissipation, but I've made a video. This is one of the velocity components here, shown in color. And our goal was to try to back out what differential equation this data was satisfying. And there was a paper by Rudy of the Brunton group showing that there was a way through matrix inversion to back out what the differential equation data satisfies. But when he applied it to fluid dynamics, Rudy found that as soon as you passed about 2% noise, the whole thing would break. The derivatives would become too uncertain, and it would not find Navier-Stokes anymore. So here I'll throw up a couple of results. So we went beyond just Navier-Stokes. Navier-Stokes is at the top. But these are the coefficients of the identified partial differential equation. So we identified 3 of them with varying levels of noise. So with all the way up to 100% noise, right? So we added, so that visually the video I showed you would be unrecognizable. We were able to recover the Navier-Stokes equation with coefficients very close to their true values. So here you would expect unity coefficients in these first 3. We've rescaled the pressure is always unity. And then the viscosity of 5 times 10 to the minus 5 is being robustly discovered as well, even though the data is horribly noisy. With the pressure Poisson equation, the Laplacian of P and the divergence of the effective term, we go up to 500% noise and still retain the equations. The energy equation fails earlier than that. You can see the viscosity coefficient. So there's 2 viscosity coefficients here. This one breaks first at 50% noise. But the point is that we can go far beyond strong form, just estimating the derivative and looking for linear dependencies with the weak formulation. One thing I'll say is that for the first 2 equations there, we can actually use integration by parts. So you can't always use integration by parts to move derivatives onto wave functions, but you can quite often. And in these first 2 equations, we can get rid of every single derivative acting on our data. So to discover Navier-Stokes and the pressure Poisson equation, we never explicitly computed a derivative of any of our hydrodynamic fields. Although we could not get around that. So in the energy equation, there's this double dot product of the gradient of the flow velocity. There's nothing you can do there to move that derivative off of that field. So you have to numerically approximate it, which is why it fails under this additive noise.
What does it mean? You're able to reconstruct with 100% noise.
Yeah.
Does it mean that the noise is basically following the Navier-Stokes equation? I mean,
no, it's noise of the so the amplitude of the noise, it's independent noise for each field. So for pressure and then all 3 components of the velocity field. It's uncorrelated, and the amplitude is, so 100% means the amplitude is exactly the standard deviation of that field.
oh, okay.
So 500% noise, we're adding noise 5 times the standard deviation of the data set.
And basically the weak formulation is able to nicely.
The weak formulation averages out over all that noise and recovers the governing equations. Yes, and actually, so for a referee, the referees for this particular paper wanted us to repeat the analysis with correlated noise, and we found essentially the same
But
thing.
if you want to explain them, the single term, so you have recognized the energy equation and the Navier-Stokes equation. The first row is all good.
Yeah, so I suppose I can do that. So the top one, the Navier-Stokes equation, we have a time derivative of our flow field as the first non-noise column. And then U dot grad U, that's the effective term. It's the nonlinearity that makes Navier-Stokes a career to solve. Grad P is the pressure gradient, and the Laplacian of U is the viscous dissipation. And then sometimes you also add a forcing in there to drive the turbulence, but this is forced by the boundaries, I suppose, in an overall pressure gradient, not a body forcing. And then the other 2 equations follow directly by taking the divergence of that top equation and taking the dot product of that first equation with U. That's how you arrive. So these are actually all logically dependent on each other in this particular case. And the incompressibility condition, which was also discovered, but I didn't bother putting it up here.
And basically the input was a 2D field,
A 4D.
a 4D.
We had
4D field.
we had full space-time risk. So we're doing these integrals not just in one dimension, we're doing the integrals in time x, y, and z. Okay, so now I'd like to change gears slightly and talk about neural networks. So the stuff I just talked about is all about approximating derivatives for sparse regression, really, which isn't a directly neural process. And when people hear machine learning, they think of neural networks by default. So when we're thinking about derivatives, the machine learning people inadvertently produced a really amazing tool, which is automatic differentiation, right? So automatic differentiation, things that you do in Python or whatever programming language you're using, when you have automatic differentiation enabled, things keep track of how they're computed. And so if you want to compute the derivative of some final quantity with respect to something that was used to construct it, it can do so recursively and automatically. It's a single function call. You can obtain any gradient that you want. It's really amazing. And so if we're trying to do a physics-informed approach where we're relating derivatives, we now have this amazing new tool where we can build a neural network, which goes from spatial or temporal inputs, goes through some hidden layers. It doesn't matter what the structure of those hidden layers are. It's completely general. And then outputs some fields. Let's say they're hydrodynamic fields. So in this case, we have a stream function and a pressure field. And now we have the ability to just compute as many derivatives as we want of any of those fields with respect to our inputs. Not with respect to the weights, which is traditionally done for network training, but with respect to the inputs themselves to actually evaluate partial differential equations on that neural representation of those fields. And an arbitrary number of these derivatives can be applied. We can go to a 6th order PDE and evaluate this perfectly fine. So you can imagine a loss of physics-informed network where the loss actually looks at, if you want to solve the heat equation, it will look at the network output and evaluate the time derivative minus the second x derivative and tell you how well your field is actually solving that differential equation, which is really amazing. And you can add other terms to the loss, things that enforce initial conditions, boundary conditions, gauge conditions. There are many modifications. But fundamentally, you could train a network with just this loss, and it will find a solution to the heat equation. Any questions on that? Okay, the last thing I want to say is that these relationships often produce conserved quantities. And in partial differential equations, conserved quantities generally look like this. They look like some time derivative of a quantity plus an x derivative plus a y derivative. And we would call F the conserved charge and G and H the current, which tells how the conserved charge how to move around locally. This is a continuity equation. Without any particular knowledge to what these fields are, I just put it in 2+1 dimensions here. But what's really interesting is things that you don't typically think of as conservation equations are conservation equations. For example, if anyone here has taken electrodynamics or is an electrical engineer, you'd probably be familiar with the Maxwell equations. So two of them tell you the time derivative of the magnetic field plus the curl of E is 0 and the divergence of B is 0. And both of these fit the form that I've written above. The divergence of B being 0 is a little interesting because it doesn't have a conserved charge. There is no time derivative of something, but it still fits that general picture of just sums of simple derivatives of quantities equaling 0. And because we can do that, you can define potentials. This is one of the main points I want to make today is that you can automatically satisfy conservation equations by defining potential fields. So in the magnetic case, you can automatically satisfy the divergence of B being 0 by defining a vector potential A and taking the curl of it. And then you can additionally satisfy the equation above by defining the scalar electrostatic potential phi. And this works for fully dynamic electromagnetic fields and is the modern formulation for electrodynamics, where you treat E and B as derived quantities rather than fundamental ones. And doing so is an abstraction for sure, but it ensures that you actually analytically solve those left equations. So if you're writing a neural network, you could imagine writing the neural network to output the vector potential and the scalar potential, and then you will automatically satisfy those equations on the left. You don't have to train the network to learn them. You just get them for free. And then when it's learning, it moves along a manifold which exactly solves those equations. So I want to talk about Navier-Stokes again and about how this relates to it, because I do a lot of 2D hydrodynamics. So the Navier-Stokes equations are completely specified here in 2D. I have a mass conservation equation. I'm thinking about the incompressible case. I have the divergence of U being 0. And then I have the nonlinear evolution equations, which we talked about before. You saw those terms, but this time we do it with forcing. But you saw all these terms in the application of the Johns Hopkins turbulence database. Okay, so just as the magnetic field being zero allowed us to write a vector potential and get that first equation for free so that we don't have to learn it, we can do that here. Oh, I guess I have a video of the equation too, if you want to see what a 2D hydrodynamic simulation looks like. So this is fairly high dissipation. So there's not many interesting features. There's not a very rich cascade. And the forcing largely determines the structure of the solutions.
So the forcing is
The forcing is
horizontal?
yeah, the forcing is horizontal, oscillating 4 times.
And that's how we get the 4 vortices there?
And that's why you see exactly that, those banded vortices in the middle. So we want to exactly solve mass conservation. We want to devise a neural network to solve these equations. Why not make our neural network learn a stream function and then just take the curl of it with automatic differentiation, and then we don't have to worry about actually enforcing this equation whatsoever. So this is exactly what was done. I took this figure from Kag et al. In physics of fluids. So they built a physics-informed neural network where they had it find the stream function. So it's ordinarily a vector in 3D, but in 2D you can write it as a scalar because it's just the out-of-plane z component that matters. And there they found the stream function and the pressure and used automatic differentiation to then evaluate the Navier-Stokes equation in vector form, where the derivatives of the stream function gave you the components of the flow. And here you can see all of the terms in the physics-informed loss, right? You have not only the PDE loss to make sure you're solving the equation, but also your boundary condition loss, your fitting of data, and your initial condition.
So what is exactly the data x, y, and t? They're not the coordinates. They're
query points. Yeah,
they are the coordinates.
they're the coordinates. So what you do is you plug in. So let's say you just pass in 3 numbers. You just pass in an x, y, and t. That will give you psi and p at that point. It's meshless. It's mesh free. You have no grid. You can evaluate at any arbitrary point, and then you can evaluate how well the Navier-Stokes equation is satisfied at that arbitrary point through the additive.
And so the weights of the network are already calibrated based on.
So the weights of the network are then trained to solve the differential equation.
Okay.
So when the network is initialized, it's certainly not going to solve your differential equation. It's going to be in some random functional representation, but it will descend through atom or whatever you want to use onto an actual solution.
And so, and what are the components of the loss function up there?
So it looks like an initial condition loss. So they were using it as a forward time integrator. So they had an initial condition loss, a data loss. I don't remember what the data loss was, a boundary condition loss, and then the PDE loss. So at least I remember what 3 of the 4. I think data loss, they used direct numerical simulation to like a coarse DNS to guide the solution towards, I believe that's what I did. I'm trying to remember. But this makes sense that you can do this and get this equation for free. So here's some examples. So I trained some pins to find stationary solutions. I said, let the time derivative be 0, find a stream function which solves these equations for this forcing. And in about 2 minutes, they will spit out equilibria configurations at whatever resolution you want. So you randomly sample 1,000 points at each training step, evaluate the PDE loss there. Here I was enforcing periodic boundary conditions.
So what do you mean for equilibria here in this case?
The time derivative of the stream function being 0. So this way you don't have to make a movie, and also it's quicker to train because there's effectively 1 less dimension in the PDE. But the structure of the network, I do want to stress that the difference in writing a network which understands dynamics and doesn't, it's just a matter of if you add a time coordinate to your input, right? Nothing about the architecture changes whatsoever other than adding an additional input for that extra dimension.
And how many layers did you use?
3.
Oh, okay. So you're not too many.
No, not particularly deep.
And how many weights did you have?
So it was 3 layers and I think 64 features per layer.
Wow.
And I mean, these particular solutions don't have, I chose a viscosity where the solutions to this equation don't have that many discernible features by eye. Something countable. And also there tends to be a lot of symmetry, right? So The part of the network which is responsible for this blue vortex here, the exact same part of that network is being used to compute this one here. So there's a lot of inherent compression in what the network is learning. And then likewise for that solution on the left, where those slightly rotated triples are likely being replicated inside the network. So one more thing I was thinking about a couple of weeks ago. This is in progress work, but I thought it'd be fun to talk about because I have one picture out of it. So the other equation, let's say I take the curl of the dynamics of U. I can write it as conservation of angular momentum, the dynamics of the vorticity field omega. And it's a little bit simpler because the pressure gradient goes away. This is also a conservation law. And so you might ask, is there a potential which ensures that you automatically satisfy conservation of angular momentum and automatically satisfy this nonlinear PDE? And of course there is, right? This is exactly the same form as Gauss's law, the divergence of B equals 0. And therefore a space-time vector potential A must exist such that the space-time curl of A automatically satisfies the Navier-Stokes equation, the nonlinear bit. It's guaranteed to exist just by the Frobenius theorem. So from this, I can make a network which, instead of learning the stream function and satisfying mass conservation, I can make one that automatically satisfies angular momentum conservation, and I can make a stream function that automatically satisfies flow conservation. And then for both of those, I can do autodiff to back out the hydrodynamic fields. And they won't agree, right? If I use autodiff for the mass conservation flow, it's going to give me some vorticity current. If I use it on the angular momentum conserving flow, it'll give me some current. So I'm going to use the apostrophes there to indicate which one came from which potential. So I have two equations being solved. Half of the network knows how to solve one exactly. The other half of the network knows how to solve the other one exactly. And then I make them fight. So you make the loss equal to just the difference of those output fields. And if they coincide, that means those potentials give rise to the same hydrodynamics, and you've solved both equations. So you've built your nonlinear differential equations directly into your network architecture. And this has the same architecture as previously described for finding the stream function and the pressure. You just input your x, y, and t coordinates, add whatever layers you want in between, and output your 4 potential components, although now it is 2 different potentials. In principle, you'd have 2 competing networks in their entirety, but I figured why not just make them the same output of the same network. So this is what happens after, the images are not as high resolution as the ones I showed from the last architecture, and it's also not perfectly trained. You can see going from left to right, I have the vorticity field, the U times vorticity field, V times vorticity field. So the top row is coming from the stream function to ensure mass conservation. This middle row is coming from the nonlinear potential, which solves the vorticity form of Navier-Stokes. And then the bottom is their subtraction with the same. I didn't plot the color bars, but the color bars are consistent among all 9 plots. And I think it's really remarkable that they converge to some kind of state, even though it's not quite as beautiful as the ones with just the stream function. All right, I'll pause here. Are there any general questions?
You are going to talk about now, because I was wondering, how can the procedure tell us if we are missing some processes or is there a way to tell by doing this that there's a disconnect in the dynamics that we.
Right, so you're talking about specifically for telling which differential equation your data is satisfying if you're missing something?
Yeah.
Yeah, so I can kind of answer that. You can plot the residual. There's a dimensionless quantity which tells you how well you're doing, where a horrible model has order 1 residual, and a good model would hopefully, if it's numerical data, should be able to go as low as possible. In practice, that's been and it kind of gives you a percentage of how much of the dynamics you're capturing with that residual. So for the experimental application, which I'm going to talk about, we got about 95% accuracy in reconstructing the dynamics. For the numerics, for the Johns Hopkins data set, we got down to 10 to the minus 4 or 10 to the minus 5, one of those. And it was a single precision calculation. So we were approaching numerical precision. for that particular application.
And how did you make it to spit equilibria?
So actually, it's funny, so that's a really good question. How did I make it spit equilibria?
Are these stable equilibrium or they're unstable?
Oh, no, they're not stable, no. So this one in particular, the left and right ones I put into forward solvers, they have, I haven't counted the number of unstable directions, but they're not stable equilibria. As for how I got equilibria, I built the network to be able to do forward time prediction, and I didn't give it initial conditions. I just told it find a possibly dynamic solution, and it wound up preferring stationary solutions because the network had to learn less.
Ah, serendipity.
Yeah, so it just found equilibria. I didn't do anything special to find equilibria. I set up the general problem, and this is what it found.
Wow, so it must be something special on the network.
I think
like,
it's because the network, there's probably a mix of reasons. I think it's because the network perhaps isn't rich enough to capture dynamical solutions in the way I've set it up.
Or the equilibria are minima of the landscape
Right.
optimized by the network.
Yeah, they must be, right.
So, somehow the network is really good at picking up, which they become local minima.
Yeah. They have some local minimum. So yeah, to train these, I did atom descent for about 10,000 steps, and then I switched to quasi-Newton to decrease the loss by another factor of 10 or 100. What am I doing on time?
You're good, don't worry.
I am worried.
Yeah, the pizza will be in time.
Okay, all right.
No rush.
So in that case, I'll try to highlight the big picture of model discovery. I won't go into all the details. If there's anything that's confusing, stop me or ask me questions at the end. I'm really excited about this. This is something I've spent a lot of time on for model discovery. So during my PhD, I worked on an active pneumatic system. So inside of your cells, making up your cytoskeleton, you have these long microtubules, these long microtubule fibers, which provide structure and play an important role in the splitting of cells and cell reproduction. So there was an idea back in 2010 or 2000, I forget exactly what year it went out. There was an idea to build a fluid almost exclusively out of just a background fluid, these microtubules, and then the motor proteins which walk along them to transport nutrients and also mediate the splitting of your cells. What would happen if you just placed a few of these ingredients that make up biology together? What would their statistical nature be? Would they do anything interesting? And they did something amazingly interesting, which is they formed an active liquid crystal. So they would collapse into these long strands via depletion interaction, and then they would consume ATP in the surrounding liquid. You can't see the motor proteins here, but they will walk along the fibers and induce large-scale motion, which is kind of remarkable.
So when you say active, this is active matter.
This is active matter,
When
yes.
active, what does it mean?
Active is energy constantly being injected into the system.
Through this protein?
So the motor proteins are consuming chemical energy in their surrounding liquid and turning it into mechanical engineering and being self-propelling. Yes.
And they propel the same fluid from which they take the energy?
Yeah, I mean, this is the geometry of this is it's in a fluid. It's between a oil-water interface sandwiched between two glass plates. So the fluid is mediating.
This is active matter, which is a very hot topic nowadays, and they have very special properties. So they behave collective behavior, is right?
Yeah.
So that's what this will be the collective behavior, is right?
I suppose you're seeing the collective behavior of these microtubule fibers in this case, undergoing large-scale motion instead of individual motion.
So energy is not conserved here.
Energy is not conserved. Energy is being injected. There's a matching between the chemical energy being consumed to inject mechanical energy and dissipation through viscosity. Okay, so I guess if I rush through this a little bit, we can apply computer vision techniques or particle image velocimetry to extract a hydrodynamic field from this video. So we take the video, we plug it into MATLAB, and it spits out.
Do you mind? Can I say that you see the black spot there? Those are called topological defects.
Yes, they are.
They are very special, is right? Because if you do the circulation of the fluid around those points, it's always a constant number.
Yes, yeah, the
churn
topological
numbers.
defects are very important. The topology of if you count the topological defects on your body, you will get the
Is all-
topological charge of a sphere. You can count, you have them on all of your fingerprints, you have those single bend defects, and in between all of your fingers, you have the triangular ones.
So there is no matter there, and those black
They're
spots,
void, yes,
they're called defect.
Mhm.
Okay?
Yes, and they are the lowest, if you assume that there's some cost to bending these fibers, it's been shown that these configurations are the lowest mechanical energy configurations. So you would expect these to spontaneously form, even if you start with a purely, if you start with all of the fibers perfectly aligned, any kick will be an instability and it will degenerate into a sea of these. And this has been well known for,
And they're very robust, is right?
they're very robust, yes.
Yes, so if you say that like the nascents are constantly extracting energy from the liquid and then using it to propel themselves, where does the energy come from?
So when the fluid is made, I believe they just inject a ton of ATP into the sample, and then eventually it eats all of it and dies. And I believe there's been some experiments to then let it die. So I believe the fibers start to detach and decay, and then people have looked at re-injecting more ATP and seeing what happens after that. So yeah, that's where the source is. It's just there initially.
That makes sense. I was wondering, so you guys are evaluating thermodynamic law.
That reminds me of Dr. Barnes, Homer Simpson, with the re-injection. You know Homer Simpson?
I do,
Simpson?
yeah.
Barnes, his boss,
Yes. Yeah.
something. Anyway,
Okay, so we can extract a hydrodynamic field for our data using PIV. And this field is noisy. I've smoothed it here for visualization, but the one we actually used for our analysis, I kept a good amount of the noise just from the PIV. And the other thing we can extract is the direction of the fibers, which form a crystalline order parameter, this director field N. So I've zoomed in on a defect. This is what N looks like. We just look at the gradient of the image and rotate it really and do some blurring. And this produces the crystalline order. And what's really interesting is you'll notice that if I just tried to use a single vector to describe the orientation of these fibers, I wouldn't be able to do it. I'd get a discontinuity along this line here, right? If they're all facing to the left, you continuously go up, they'd all be facing to the right on the top. And so this can't be an ordinary vector field, this director field. It's a really bizarre one. We have two vector fields U and N. Can we learn all of the governing equations? Can we learn the PDEs that describe what they do, how they interact?
just remember, N is the direction of the
Yes,
fibers.
N is the direction of the fibers, U is the flow velocity. And we want to do this in a way respecting the symmetries. I didn't get to talk, just because of time, too much about how to enforce symmetries directly. There's a whole field of group equivariant neural networks, which, for instance, directly enforce your library or your symmetries. But here we have three that we want to assume, which are translation. It shouldn't matter. The equation shouldn't depend on where I look in the sample other than what the orientation of the fields are. I expect rotation and reflection symmetry, just looking at the data. And there's this nematic symmetry, right? So I'm going to declare the director field N is equivalent to its negative. The axis of N is what's important, not the direction. I have this head-tail symmetry in my system. And this is important. So my PDE has to respect this head-tail symmetry. If it breaks it, then I wouldn't see these topological defects. You can infer from the defects that this symmetry exists. Okay, so the whole idea is that we want to search for a zero. Every equation ever can be written as a sum of things equaling zero. If you have A equals B, just subtract B from both sides. So we want to find a sparse sum of interesting functions using our data which equals zero. And we're going to assume locality. We'll assume some principles from physics like locality, so that F should be a local function. We shouldn't be multiplying the flow velocity here and here. It should be a local object. Translational symmetry tells us that any coefficients in our model should just be constants. They can't have any inherent spatial temporal dependence. And the rotation and nematic symmetry are really interesting, and I don't think I have time to tell you exactly what they say. But they tell you that all Fs have to belong to the same irreducible representation of those symmetry groups. So irreps are the most fundamental spaces on which symmetries act that cannot be broken down any further. And this is where all physical laws live, is inside of irreps. So what you can do is you can conjecture different transformation properties. So the easiest transformation is just that F doesn't transform at all when I do rotations or this nematic transformation. That would correspond to scalar differential equations. But you could imagine vectors, higher rank tensors, both in the nematic order parameter and in the rotation space. So we have a symbolic alphabet. We have, so that this is A, our symbolic alphabet. We have a gradient operator. We take spatial gradients. We can take a temporal gradient. We can take and we can apply these to the flow field, which is a vector field, and N, which we're going to treat as a vector field for these purposes, even though again, it has that nematic symmetry. And we're going to construct every possible vector, scalar, and tensor up to some order that you could possibly make out of these objects that respect symmetry. So if I just want a vector that could appear in a vector equation, you could imagine doing u dot n times n dot grad n. That's a perfectly valid nonlinearity that can enter into a vector equation. Who's to say this isn't the fundamental term that needs to be in our vector equation to make the dynamics work? Outside of symmetry considerations, we have no reason to discard this term. And so we do, we constructed everything. So this is one of the libraries. We looked at 6. So this is the one that considers, so I introduced some shorthand here and I put everything in index notation just for my own sanity. But there's roughly 60, if you go up to second order derivatives, there's roughly 60 vector fields that you can make out of these data and their gradients. Most liquid crystal models only contain about 8 of these 60 possibilities because people's imaginations can't, I don't know, they don't think to include anything else. And then overall, there were 126 tensors that form a systematic basis for all physics up to this second order cutoff. Every physics equation to lowest order has to live in this space. And so now we do the weak formulation. So I talked about applying derivatives to noisy data often gives you junk. So instead, we're going to do the integrals of those derivatives with these weight functions that we know exactly. So we're looking for not a sum of f's, but a sum of integrals of f, which equals 0, to mitigate this noise. So this is the rough picture. We compute every term densely so this is 3-dimensional data because we have 2 spatial dimensions and 1 time dimension. We do pointwise multiplication by a weight function. So here you can see our weight function vanishes at the boundaries, just like that 1D case. And then we do numerical quadrature. So we do the Riemann sum in all of those directions. And this constructs a single element of a huge matrix, where each column of the matrix corresponds to a different term that could be in our equation. For 3+1D data, for the Johns Hopkins data set, each element of this matrix was roughly the sum of 1 million spacetime points. So we're doing a substantial amount of averaging. Luckily, computers are fast.
So the G matrix is the same size as the grid.
The number of columns corresponds to the number of terms that could be in the equation. The number of rows. So something I didn't talk about here is when you do the weak formulation, you have to pick a bunch of boxes to do the integrals with respect to. So the number of boxes is the number of rows.
Okay, is the length of the.
So this is for 1 box. I've picked 1 box of space-time data and computed this integral to get a single element of G. Then I would pick a different box and I'd work my way down this column vector. And that's how you construct it. And then we have a sparse regression method to determine if there's any insignificant coefficients based on the singular value decomposition. So from this, and we've accelerated this to a great degree, so we can now in semi-real time consider libraries of well over 1,000.
Can you tell a little bit more? Like, do you know about sparse optimization? Maybe if you can.
Yeah, so of this huge set of terms, most of them will not matter, right? So the physics will likely be described by just a handful of them interacting, not all of these. And so we need some way to determine which ones are irrelevant and don't need to be included in the model. So sparsity is finding the few small set of meaningful parameters in the model. So by computing the singular value decomposition, which is a common data compression technique, we can use the singular value spectrum to determine which terms we can throw away without significant impact to the model. So to close out, we found 9 partial differential equations that describe our data, all of them fairly simple, the longest one being the Barris-Edwards equation, this one here, which has been well known in the literature for about 100 years. It's really interesting to do the discovery of this equation and then go look up what it is. And they're not all physically independent, right? So I've color-coded them here based on which ones are logically equivalent to each other. So there's 3 classes of PDEs, so we can logically reduce this down to a
How
level.
did you split single equations? Because the initial your initial condition is you do a super linear.
Yeah, so you do this SVD loop where you throw out terms.
Oh, the eigenvalues.
And then once you get a satisfactory sparse model, you take the most important term in this equation and throw it out, and then try again. And you can iteratively search for as many equations as you want.
Each singular vector will give you one equation, basically.
Each singular vector with a really small singular value gives you roughly one differential equation that describes your data. So we got those. We reduced them down to I swear I'm almost done.
Take your time, don't worry.
So we boiled those down to the three fundamental equations if we were to communicate this, which are mass conservation, flow alignment containing the time evolution of n, and also this bizarre constant extension requirement involving the dot product of the gradient. So A here is the symmetric gradient of U, the strain tensor.
So you didn't recover any Navier-Stokes equation. There is no momentum equation.
No, yeah, so that's actually something I should have mentioned at the very beginning. So that video I showed you was sped up quite a bit. It's an incredibly slow creeping flow. And so there are negligible inertial effects. Yeah, so we didn't really expect necessarily to find the nonlinearity of Navier-Stokes.
So Windy, the second equation, no, you call it a flow alignment equation. So the first one is a mass conservation, which is
Yes.
The second one is telling what?
So the second one here is so this is the effective derivative, right? So this is you're being advected by the flow. This term here is co-rotation. So if you have a vortex, the flow is going to want to rotate with the vortex.
Okay.
And then this last term here is the flow alignment term. So this tells you if you have an extensile flow, if you have a hyperbolic flow, how does it want to rotate in that hyperbolic flow?
Remember that n is the orientation of the fibers.
Yeah.
So basically the fibers are advected by you, and then they can also spin by the vorticity of the fluid.
Exactly. Yeah.
And the other term is basically how do you?
I can draw a real quick picture. It's if you have a flow that looks like this, does the fiber want to point this way or this way? If you let it come to rest. So there's no vorticity here, but how does a symmetric flow gradient make it tumble?
And the last one?
That's the last one, is the
constant extension. Oh, yeah.
Oh, you're talking, sorry, yeah.
Yeah.
Extension. This is the analog of the Stokes equation, is what I would.
That is the analog of.
What's interesting is it's actually 1 degree, it requires one derivative less than the Stokes equation. So what's possible is that, so also all of this was excluding data from your defects since we didn't have meaningful data there. It's possible that we would need to generalize it with one higher derivative in order to match your defects.
It's kind of an energy, there is no energy conservation.
So that E is measuring the rate of energy injection into the
Okay,
system.
so
So
that
we get a direct measure of activity.
So E is basically dEdt is a.
It's a time scale with which things are injected in. So
Which basically show that the system doesn't conserve energy.
so this explicitly breaks time reversal symmetry and shows that your system has some non-trivial motion going through.
Beautiful.
And then we can do so the left is our experiment. I've plotted the director field and I forget what the color is underneath. I think one of the things squared. So the left is directly from experiment and the right is our simulation using the equations we discovered and boundary conditions from experiment.
And they are very accurate.
Pretty good. I mean, we go well beyond correlation time here, so there's a little difference at the end, but by and large, I was happy with this. Yeah, so I'll leave up other applications of this technique. I don't think I said this technique is called Spider, but we've applied it to highly noisy numerics and also a few experiments now. So I'll end with that.
Thank you. So, any questions from our virtual friends? Huh? Someone online that wants to ask some questions? Okay, so what about here in the audience? Do you have any questions? Okay, thank you. Okay, now we go downstairs and there will be some pizza, so we can enjoy some pizza all together, okay? Thank you for coming.
That's not an excuse.
Okay.